So I'll be discussing how to predict the tidal stripping of dwarf galaxies today. And the main question that I'm concerned with is the survival of substructure. So are you able to kill dwarf galaxies? So we want to know how low mass galaxies respond when they're evolving around a Milky Way host with a disk. And these low mass galaxies are less than 10 to the 9 solar masses, so we're concerned with dark matter only. Our simulations don't have any stars, but that's okay because these galaxies have such low masses that they would have very little luminosity, if any. And so to do this, we use controlled n-body simulations. And this has been done in the past, and this paper right here by Hayashi has shown that with time, density profiles of satellite galaxies decreases. And as you can also see, it depends on the pericenter of the satellite galaxy to the host. So these solid lines have closer pericenters than the other line styles, and you see that they are destroyed even more. And the outer regions are preferentially stripped, while the inner regions retain their central slope. So this shows that dwarf galaxies are stripped from the outer regions, but in their work they found that these satellites could eventually be destroyed, so you could completely destroy the galaxy. And another way to look at this is through the circular velocity profile. You see that the profile retains its shape, but decreases with time. And the Vmax systematically decreases, but you see the profile is the same, and the satellites are destroyed. And in much more recent work, in Jorge Peñarrubia's 2010 paper, they looked at how density profile evolves with time for different cusp and core models. And you can see that there's a sharp decrease in the outer regions of an NFW profile, but they found that in fact, if you have a central constant density core, you're able to unbind the satellite and have it become completely destroyed, but cuspy satellites aren't completely destroyed. And you could look at this in another way by imagining how the mass evolves with time, and these greenish dots are the ones that have central constant density cores, and they are more preferentially stripped. And you also notice that including a disk in the Milky Way is important. You have significant mass loss, and larger pericenter to apocenter ratios are also important. However, in this work, they found that you didn't destroy the satellite completely with an NFW profile. So what we've done is we've examined the evolution, the tidal evolution of satellites using Miguel Rocha's spheric code for initial conditions. And we have two dwarfs, the 10 to the 8 and a 10 to the 9 solar mass dwarf, and these are dark matter only, as I mentioned. And we have very high number of particles. We have 54 million particles in each of these dwarfs with a frozen external potential Milky Way. And that means that the minimum mass in our dwarfs is 13 solar masses. So we have really high resolution, so we're able to track these guys for a long time on order 10 to the 6, on order 6 gigayears or more. And so we can see, are these dwarfs actually completely destroyed ever? To show you what these initial conditions look like, here's a 10 to the 8 solar mass dwarf. And you see the initial NFW profile is a solid line. And from this NFW profile, the initial conditions are sampled, and the blue line is almost exactly on top of this NFW profile. And after evolving in isolation for 2 gigayears, the final profile is shown in red. So these initial conditions are very stable. And in circular velocity, you can see that as well, where the difference is less than half a kilometer a second in the very center region. And as a note, this is the force softening boundary.
So how did you set that initial condition up? You solve for?
So it samples from the distribution function. Yeah. And just real quickly, you can see that the 10 to the 9 solar mass dwarf behaves well as well. Yep. So just an advertisement for previous work. In Arraki et al. 2012, we started looking at tidal stripping, but in the context of the too big to fail problem. So we looked at how baryon removal and tidal stripping impacts the survival of dwarf satellites, and if that's able to bring these massive failure galaxies into agreement with the local group dwarf toroidals. So here you have local group dwarf toroidal points. in these squares, and the massive failures from the boiling Coltrane et al. Work from the Aquarius simulations. And we find that using two different mass removal methods, which are these solid black lines, we indeed lower the circular velocity profiles of these galaxies so that they're able to come into better agreement with observations of the local group dwarfs. And that furthermore, tidal stripping with including a disk component substantially reduces these profiles. So we find that baryons are indeed extremely important. Even if you don't create a core, you need to include baryons if you're trying to talk about, are there too many massive dwarfs in an n-body only simulation? You really need to examine baryons. So from this problem, we continued working on tidal stripping. And here, when we set up an orbit, we place our initially isolated dwarf galaxy in this potential of the Milky Way. And we include a disk component. The blue dot is just the center of the Milky Way. And here are all the particles of the dwarf galaxy. We simulate a range of pericenters to examine how tidal stripping differs, but we fix the ellipticity of the orbit so that the apocenter-pericenter ratio is always 1:6. And all of these orbit for at least 6 gigayears, so we're able to have substantial number of orbits. So what we're trying to, the main points we're trying to get at are how do satellite galaxies evolve with time? We want to understand, are they able to be destroyed? And if so, will this impact the possible dark matter annihilation boost signature that you would predict? Because if you destroy these satellites completely, that would alter the calculation. And are we able to make predictions for what tidal stripping will become based on these simulations? And it would be awesome if we did this based on as few parameters as possible. To show you how these dwarfs satellites evolve with time, we have radial distance from the host. So this is far away initially. And then with time on this axis, it continues to orbit, and pericenters are marked in blue. And I'll show you the mass loss with time. So you see that, first of all, this object has a huge decrease in mass. So 5 orders of magnitude over 6 gigayears. So that's extremely high amounts of mass loss. And at each pericenter, there's a really dramatic decrease in the mass of this galaxy. But also, it's not completely flat in this region between. So at apocenter, there is still some change in the mass profile. So we're going to want to look at a more robust parameter, which we found to be Vmax. So just as a note, whenever you see this star, I'm looking at the same object, so it can kind of help you keep track of all these different parameters for one simulation run. So for this same run, you see that Vmax has more of a stair-stepping feel, and that at apocenter, it's pretty constant. So Vmax is going to be a good proxy for understanding what's going on with the tidal evolution. And now if you plot a lot of other objects, we have the one we were just looking at is this bottom line. In terms of number of orbits they've completed instead of time, so that they all line up with their pericenters and apocenters at the same location. So marked in red are the apocenters. You can see that they all exhibit the same stair-stepping, and that they really do have significant mass and reductions in Vmax. So this is really interesting, and we want to put it in context of central density as well. So here's the evolution of the density profile for one object as it evolves in time. And you see the outer regions are significantly reduced immediately. However, the central slope stays really constant, and it doesn't change much except for a normalization that brings it down. So one thing to notice is that I have the scale radius of the NFW halo marked here, and I have the tidal radius marked right here as well. And the tidal radius is calculated to find out the tidal radius when the object is at pericenter. So this will give you an idea of how much mass loss or to which radius this object will be stripped. And you see that because the tidal radius is 1.5 times the scale radius in this case, it's significantly tidal stripped in the outer regions. There's a lot of mass loss, but it's not completely destroyed. So next, I'm showing you this same dramatic case, and it has a lot more mass loss really quickly. It's a little bit slower, just so you can catch it all. And you can see that the mass is really removed quite quickly from these outer regions. Bound material comes back and forth, but it does continue to decrease, and that's because the tidal radius is now within the scale radius. The tidal radius is 1/2 the value of the scale radius. And so as we continue in time, we find that the center region decreases, but we no longer resolve the region where the inner density is constant and normalized just down a little bit. So what do we want to call this? Do we want to call this object completely destroyed? No, we can still track it. It still has over 200 particles associated with it, and it seems that this object still persists even after this dramatic tidal stripping, so we don't find that objects are completely destroyed. Another way to think about this is in terms of that scale radius and tidal radius values that I showed you. So here, you can parameterize each simulation by the tidal radius over scale radius fraction, so you can see how tidally stripped this object will become. And we find that both mass fraction and Vmax evolve in a predictable way with tidal radius in our previous work, so we want to examine if this scatter between all these points of the same tidal radius is due to the number of orbits they've completed. So that's what we've investigated in this part. And for this one object, we're going to look at how RTRS how the mass changes with RTRS. So what I want to show you is this is the same object, and one object exists in a vertical line in our TRS space because we fixed its scale radius from its initial value and the RT value from the pericenter. So this is always fixed for all these, for one simulation. So you can think of this is the tidal radius it's going to be stripped to, and that was its initial scale radius. And next, each point on that line is a subsequent orbit. So this is the first orbit, this is at the second apcenter, and so on and so forth. So if we look at all the objects after they've completed their first orbit, regardless of mass, so the blue is the 10 to the 8 and the red is the 10 to the 9 solar mass dwarf, when you divide by their initial mass, they all lie on this line. So that's pretty interesting. Let's see if it happens for the next orbits. We find that orbit 2, 3, 4, and 5, they all exhibit the same behavior. So what we're finding is that we're able to predict tidal evolution of these dark matter only satellites regardless of their total mass. We can see that the mass fraction depends only on the RTRS value. And this is just to remind you that even after the 5 orders of magnitude reduction in mass, this object was not completely destroyed. So what we're working on is trying to predict what other RTRS values, how their mass will change with time. So that's what we're currently working on. And we find that actually Vmax behaves in a very similar way, and we could also use that as a proxy. So altogether, we're interested in studying how tidal evolution changes the mass and Vmax profile of a dwarf, and if we're able to predict that and use those predictions. And we find that dwarfs are not completely destroyed, even though we had very high resolution and we followed these dwarfs for a significant period of time. They weren't completely destroyed, but they always had some bound clump material in the center. And this means that the annihilation dark matter boost factor doesn't have to be changed. So to finalize, we find that tidal stripping can be predicted by the bound mass or the Vmax fraction of the halo, which depends on the RT-RS, so the pericenter and the scale radius of the galaxy. Thanks.
So in your initial setup, and you say it is in a Milky Way potential well. Mm-hmm. So do you really include the disk potential as well?
Right,
so
yes.
There's a shock when it comes to...
No, so we approximate it with a spherical disk, so everything is just...
still spherical and
yeah.
Smooth. Everything is smooth.
Yeah,
okay.
But the disk mass is 6 times 10 to the 10 solar masses, so, and it has the exponential profile.
Right. But the second question is that how do you, you're finding, this Hayashi has some fitting formula, and that certainly is useful. But according to your simulation, how far is it significantly different from his, or actually it's more or less similar?
Right. So those were predicting how bound mass and Vmax are related. It's everyone finds the same thing, that mass is proportional to Vmax, so like the 3.5.
And the truncation radius is more or less the same?
Yeah, so we always find that the mass-Vmax relation is similar, and we're working on other parameters like RS, how that changes with time, to see if they fit the same as the Hayashi and Penrubia curves. But your last question was?
Well, last question is that, of course, this is not a realistic in a sense,
Mm-hmm.
because if you have a clumping disk, and then in fact, then you could probably have a harassment, and that may, I don't know how to make this connection. Certainly this is very, very interesting. But, when we apply to realistic halos, where it is clumping, and you have a disk, the disk.
Well, yeah, it's a minimum,
Halos
right?
are
So.
clumping. Yeah, you have a lot of subhalos.
Very small fraction of weight.
Well, then if you run into it, it will get shot, especially the disk itself. If you run into
If you go
it will be shot.
at an inclination,
Your base is 10 kilopascal. There is no mass of the disk.
Well, okay, so that's.
it'll be a lower limit, but yeah, that's another thing to consider.
First, I want to confirm my understanding of your last talk. It seems to me the mass of the satellite galaxies does not only depend on where the satellite is, but also the number of orbits that already constructed.
Mm-hmm.
So that's hard for me to understand because here you don't have a dynamical friction.
Correct.
But when you have dynamical friction, then the orbital decay may be faster.
So these are low enough mass that I don't think they'll be subject to dynamical friction significantly.
How I generalize your result to slightly more massive.
Slightly more massive. So in our previous work, our dwarf was initially 3 × 10⁻⁻⁻ solar masses. And I've started just this week looking at how those results compare with these results. And actually, it fits on that line pretty well. So in...
When you run into the regime where dynamical friction is a factor,
Mhm.
then the number of orbits will significantly change for a given orbital radius.
So if you know what the pericenter is, you could recalculate the tidal radius that it would have initially, and if you pick at each, like at the first orbit, you know what that pericenter is. You could use this to predict, I know the pericenter, and I know how much dynamical friction will contribute. I can recalculate the tidal radius, and maybe you'll be able to, we could look at that and try to see if you put that, at the second orbit, it'll be here. You could move it in our TRS space, but know where it should be. Yeah, we could look at that.
But this is a fixed potential, right?
Yeah, this is.
So if you allow live particles in your potential, will that change your result?
I'm not sure. We haven't looked at it.
Yeah, because then you could have some back reaction or this kind of.
But look, in that field that studied lengths, the dynamical friction, for example, doesn't depend on the feedback.
No, it's not only dynamic friction, but other things like
Which don't depend on feedback. There's no back reaction from on dynamical friction.
Well, you could have some kind of even resonance to some way, right? Because you have particles in your orbital particle, and then you have particle in your I don't know. It's a long term, could have some long term secular evolution kind of stuff. I don't know.
People try to do it and never see it. I mean, we've done it with the plane.
Oh, yeah.
Okay. Any other questions? Kenza? Otherwise, let's thank her.